Hello students, welcome to Saurav Sir's classes. This video is Inequalities Part 4. Now in the previous video, that is in the Inequalities Part 3, we learned about some of the theorems on inequalities. Now in this video, we will continue learning some other theorems based on inequalities. Now, let's start with our theorem. So let's start with the theorem number 4, which is if A1, A2, so on till An, if they are n distinct positive real numbers, so they are n distinct positive real numbers, and let P, Q and R, let P, Q and R be natural numbers, so they are natural numbers, then we would have our A1 raised to the power P plus Q plus R plus A2 raised to the power P plus Q plus R plus so on till An raised to the power P plus Q plus R. So all of this divided by n. So basically it is the arithmetic means of these positive quantities raised to the power P plus Q plus R. Or it is the arithmetic mean of the P plus Q plus Rth powers of the n distinct positive real numbers. So this is greater than A1 raised to the power P plus A2 raised to the power P plus so on till An raised to the power P divided by n, this into A1 raised to the power Q plus A2 raised to the power Q plus so on till An raised to the power Q divided by n into again A1 raised to the power R plus A2 raised to the power R plus so on till An raised to the power R, this divided by n. So this is the theorem. So what we have here is the arithmetic mean of the P plus Q plus Rth powers of Ai. This is greater than the product of arithmetic mean of Pth powers of Ai into arithmetic mean of Qth powers of Ai into arithmetic mean of Rth powers of Ai. So this is the theorem. Now let's go to theorem number 5, which is Weierstrass inequality. So this theorem states that number 1, if A1, A2, so on till An, if they are n positive real numbers, so if A1, A2, so on till An, if they are n positive real numbers, then for n greater than equals to 2, we will have 1 plus A1 into 1 plus A2, so on till into 1 plus An. This would be greater than 1 plus A1 plus A2 plus so on till plus An. And next is if A1, A2, so on till An, if they are positive real numbers less than unity, if they are positive real numbers less than unity, that is less than 1, that is if this A1, A2, so on till An, if they lies in the interval of 0 to 1, where I runs from 1 to n, so if these AIs are runs in the interval of 0 to 1, that is they are positive real numbers less than unity, then we will have 1 minus a1 into 1 minus a2 into so on into 1 minus an. This would be greater than 1 minus a1 minus a2 minus so on till minus an. So this is the Weierstrass inequality. So it states that if a1, a2, so on till an, if they are n positive real numbers, then for n greater than equals to 2, we will have 1 plus a1 into 1 plus a2, so on till 1 plus an. This would be greater than 1 plus a1 plus a2, so on till an, that is plus an. And similarly, if a1, a2, an, if they are positive real numbers that are less than unity, that is they lie in the interval from 0 to 1, then we would have 1 minus a1 into 1 minus a2 into so on till 1 minus an. This would be greater than 1 minus a1 minus a2 minus a3 so on till minus an. The next theorem, that is Cauchy-Schwarz inequality, this states that if a1, a2, so on till an, and now we have b1, b2, so on till bn. So a1, a2, so on till an, and b1, b2, so on till bn, if they are 2n real numbers, so if they are 2n real numbers, then we will have our a1 b1 plus a2 b2 plus so on till plus an bn whole square. This would be less than equals to a1 square plus a2 square plus so on till plus an square, this into b1 square plus b2 square plus so on till bn square. So we have if a1, a2, so on till an, and b1, b2, so on till bn, if they are 2n real members, such that then we would have a1 into b1 plus a2 into b2 plus so on till an into bn whole square. This would be less than equals to a1 square plus a2 square so on till an square. This whole would be multiplied by b1 square plus b2 square so on till plus bn square. Now here an equality sign would hold, that is a1 square plus a1 b1 plus a2 b2 plus so on till an bn whole square. This would be equal to a1 square plus a2 square plus so on till an square whole multiplied by b1 square plus b2 square plus so on till bn square. So equality will hold if and only if and only if we would have our a1 by b1, this would be equals to a2 by b2, which would be equal to so on till an by bn. So when this would hold true, then only there would be an equality sign. Otherwise it would always be less than. So this is our Cauchy-Schwarz inequality. Now next we will go to the next theorem. Now next we have Chebyshev's inequality, which here it says that if a1, a2, so on till an, and b1, b2, so on till bn. So if a1, a2, so on till an, and b1, b2, so on till bn, if they all are real numbers, so they are real numbers such that we will have a1, so such that a1 is less than equals to a2 is less than equals to a3, so on till it's less than equals to an. Similarly, b1 is less than equals to b2 is less than equals to so on till less than equals to bn. Then we would have, so then n into a1 b1 plus a2 b2 plus so on till plus an bn. This would be greater than equals to a1 plus a2 plus so on till an into b1 plus b2 plus so on till bn. Or this would imply a1 b1 plus a2 b2 plus so on till plus an bn divided by n. This would be greater than equals to a1 plus a2 plus so on till an divided by n into b1 plus b2 plus so on till bn divided by n. So what we have here is that the arithmetic mean of AIBI, where I runs from 1 to n. So arithmetic mean of AIBIs, this would be greater than equals to the product of arithmetic mean of AIs and arithmetic mean of BIs. So Chebyshev's inequality says that the arithmetic mean of AIBI or AI into BI, this would be greater than equals to arithmetic mean of AI into arithmetic mean of BI.